Hello everyone, my name is Kishan Agarwal. Today I'm going to present my Tech Talk video of data structures. My topic is multiphase sorting. So, what is sorting? In computer science, a sorting algorithm is an algorithm that puts elements of a list into an order. The most frequently used order are numerical orders and lexicographical orders, and either ascending or descending orders. Efficient sorting is important for optimizing efficiency of other algorithms such as search and merge algorithms that requires input data to be in sorted lists. Sorting is also often useful for canonicalizing data and for producing human readable output. Formally, the output of any sorting algorithm must satisfy two conditions. The output should be monotonic order, that means each element is no smaller or larger than the previous element according to the required order. The output is a permutation, that is a reordering yet retaining all of the original elements of the input. So classification. Let us see what are the classifications of sorting. Sorting algorithm can be classified by computational complexity, that is best, worst and average case behavior in terms of size of the list. For typically serial sorting algorithm, good behavior is big O of n log n, with parallel sort in big O of log n square, and bad behavior is big O of n square. Ideal behavior for a serial sort is big O of n, but this is not possible in the average case. Optimal parallel sorting is big O of log n. Swaps for in-place algorithm. Next is memory usage and use of other computer resources. In particular, some sorting algorithms are in place strictly. An in-place sort needs only big O of one memory beyond that items being sorted. Swaps for in-place algorithms. Recursion. Some algorithms are either recursive or non-recursive, while others may be both. Example, merge sort. Next classification is based on stability. Stable sorting algorithms maintain the relative order of the records with equal keys, that is values. Next, whether or not they are comparison sort. A comparison sort examines the data only by comparing two elements with a comparison operator. General method, that are insertion, exchange method, selection, merging, etc. Exchange sort includes bubble sort and quick sort. Selection sort includes cycle sort and heap sort. Whether the algorithm in serial or parallel. The remainder of the discussion almost exclusively concentrates upon the serial algorithm and assumes serial operators. The next is adaptability. Whether or not the of the inputs affect the running time. Algorithm that takes this into account are known as adaptive algorithms. Online. An algorithm such as insertion sort, that is online, can sort a constant stream of input. Stability. Stability sort algorithms sort equal elements in the same order that they appear in the input. For example, in the card sorting example, the right to the right, the cards are being sorted by their rank and their suit is being ignored. This allows the possibility of multiple different correctly sorted versions of the original list. Stable sorting algorithms choose one of these algorithms according to the following rule. If two items compare are equal, like the two 5 cards, then the relative order will be preserved. That is, if one comes before the other in the input, it will come before the other in the output. So stability is important to preserve order over multiple sorts on the same data set. For example, says the student record consisting of name and class section are sorted dynamically first by name, then by class section. If a stable sorting algorithm is used in both cases, the sort by class section operation will not change the name order with the unstable sort. It could be that sorting by selection shuffles the name order, resulting in a non-alphabetical list of students. So multiphase sorting. Multiphase sorting or merging is another name for an unbalanced merging technique. It is not the same as 3-2 or 2-3 or 2-1 1-2 type of unbalanced merge. In a 4-tape multiphase merge, such as the program implemented sort 2, there would always be 3 input units and 1 output unit. The name multiphase was chosen because in using this technique as the external merge portion of a tape sort, many passes are required to produce a sorted string of records. A phase in multiphase sorting, however, does not process all of the data records in any pass except in the final pass, which is the same as the three-way merge. The internal phase of sort 2 was altered only in the respect of producing shorter tape blocks than would be normal of a T by 2 merging phase. The actual difference in the length of the tape record produced by the internal phase for a 4 tape T by 2 merging phase and the 4 tape multiphase was the tape record corresponded to the size of a tape record length that would be accommodated on a 6 tape T by 2 sort. So the reason is that for a 4 tape T by 2 sort, the number of input output areas needed is 3, whether for a 4 tape multiphase merge the number of input output areas is 4, the same number as the 6 tape T by 2 sort. The final result of this approach, as far as actual sorting timing is concerned, is little, if any, different from the approach to outside output string from the internal sort in some special sequences. The chance for obtaining one of the ideal values as the total number of strings produced by the internal sort is small as the size of the data file increase, assuming random input records. The internal phase writes the string produced on the output tapes in the same manner as for a T by 2 sort, that is, the string produced by the internal sort are written alternatively on the output tapes. No special scheme of the output record is used. However, it is possible to alter the internal phase so that the output is written on T1 tapes and number of strings per tape would approach the ideal number. This table shows the multiphase sorting algorithm. So as we know that there are some simple sorts. Two of the simple sorts are insertion sort and selection sort, both of which are efficient on small data due to low overhead but no efficient on large data. Insertion sort is generally faster than selection sort in practice due to lower or fewer comparisons and good performance on almost sorted algorithms, and thus are preferred in practice, but selection sort uses fewer writes and thus is used when we write performances is a limiting factor. So insertion sort is a simple sorting algorithm that is relatively effective for a small list and mostly sorted list, and is often used as a part of more sophisticated algorithms. It works by taking elements from the list one by one and inserting them in their correct position into a new sorted list, similar to how we put money in our wallet. In arrays, the new listed and remaining elements can share the array space, but insertion is expensive, requiring shifting all following elements over one by one. Next is selection sort, which is also an in-place comparison sort. It has big O of n square complexity, making it inefficient on large lists and generally performs worse than the similar insertion sort. Selection sort is noted for its simplicity and also has performance advantages over more complicated algorithms in certain situations. Efficient sort are merge sort, heap sort, quick sort. So merge sort takes advantage of ease of merging already sorted lists in a new sorted list. It starts by comparing every two elements, that is 1 with 2, then 3 with 4, and swapping them. It first should come after the second. It then merges each of the resulting list of 2 into lists of 4, then merges those lists of 4, and so on until at the last two lists are merged into the final sorted list. Similarly, heap sort is a much more efficient version of selection sort. It also works by determining the largest or smallest element of the list, placing that at the end or beginning of the list, then continuing with the rest of the list, but accomplishes this task efficiently by using a data structure called heap, a special type of binary tree. Once the data list has been made into a heap, the root node is guaranteed to be the largest or smallest element. When it is removed and placed at the end of the list, the heap is rearranged so the largest element remaining moves to the root. Using the heap, finding the largest element takes big O of log n time instead of big O of n for a linear scan, as in simple selection sort. This allows heap sort to run in big O of n log n time, and this also the worst case complexity. Next comes quicksort. Quicksort is a divide and conquer algorithm which relies on a partition operation to partition an array. An element called a pivot element is selected. All elements smaller than the pivot elements are moved before it, and all greater elements are moved after it. This can be done efficiently in linear time and in place. The lesser and greater sublists are then recursively sorted. This yields average time complexity of big O of n log n, which low overhead, and thus this is a popular algorithm efficient implementation of quicksort. With in-place partitioning are typically unstable sort and somewhat complex, but are among the fastest sorting algorithm in practice. So next, when discussing about multi-phase sorting, sort 2 made use of intermediate phase distribute the string contained on the two list output tapes of the internal phase to three tapes, which will then be used as input tape to the multi-phase merge. The intermediate phase, called the adjustment phase, is based on an elementary polyphase merge sort algorithm developed by S.W. Reynolds. As an example of how the adjustment of strings on two tapes on three tapes work, assume that the tapes available are 1, 2, 3 and 4. The output tapes are internal phase are 3 and 4. 1 and 2 are work tapes. The number of strings of each tape, which is essential for the successful operation of the multi-phase operation, are found in multi-phase table, which I have shown here, which consist of the following terms, that is AI, BI and CI, the number of strings to be merged after the adjustment phase. So initially the values assigned to AI, BI and CI are n and n are I1 and 3 respectively. To reach the next level, higher level, the next AI is the previous CI. The next BI is the sum of the previous AI and CI, and the next CI is the sum of these previous BI and CI. N is always the sum of the current, that is BI and CI. The tabular values which corresponds to the first n plus 3 ci, which is equal to or greater to s. The total number of strings produced by the internal phase are used in computing the adjustment values. If s is 6 or less, special values are assigned by the program. The adjustment values are pi, the number of strings to be copied from 4 onto 2; p2, the number of strings to be copied from 4 to 1; pa, the number of strings to be copied from 3 to 1. The number of string x is the number of strings to be copied two-way merged from 3 and 4 onto I, and y is the another string to be three-way merged from I, 3 and 4 onto 2. Other terms used in the following equation which require definition are: a, the number of strings on 4 prior of the adjustment phase, s by 2, and k, the difference between the number of strings on 3 and 4 prior to adjustment phase, that is either 0 or 1. So the formulas which are used for adjusting the number of strings on each step are: y is equals to s minus n by 3, x is equals to s minus n minus 2y, p1 equals to c1 minus y, p2 is equals to a minus x minus c1, p3 is equals to a3 plus k minus x minus y minus a1. This is the tree diagram showing the multiphase sorting. Thank you.